Hey everyone, welcome back. So one of the things I've realized throughout this project is that ambitious ideas have a way of changing the people who pursue them. Not because the process is easy, but because difficult projects force growth in ways that comfort never will. So over time, the failures and iterations and problem solving and constant learning slowly compound into something larger than the project itself. And honestly, that's become the real story of HarmonicAF. So over the past couple of years, HarmonicAF has slowly evolved from a simple prototype in version 1 into a design build project much larger than I originally expected. What started as a cool idea for a harmonic drive system eventually turned into a deep dive into design, manufacturing, material science, process control, and learning along the way to make the idea realized. So a huge amount of what became HarmonicAF version 2 was shaped not only by lessons learned from the original prototype, but also by feedback, ideas, and discussions from all of you in the comments and Discord. So version 2 has been almost completely re-engineered around compact packaging, structural performance, manufacturability, advanced features, and long-term usability. So in this series, I want to share that journey. This first video is really about how HarmonicAF evolved from an idea into a manufacturing process. My name is Doug, and this is AstroAF. Sometimes, cool ideas turn into much larger projects than you ever expected. What originally seemed like a straightforward enclosure print slowly evolved into a much deeper engineering and manufacturing problem. Over the course of nearly 2 years, HarmonicAF forced me to continuously learn new skills just to keep moving forward. At some point, even learning fusion stopped being optional and became one of the most useful engineering skills I've developed throughout this project. And honestly, there were moments where HarmonicAF occupied more mental bandwidth than was entirely reasonable and perhaps healthy. But I think that's part of the process. Ambitious ideas have a way of demanding transformation from the people who pursue them. In hindsight, a certain amount of naivety was probably required to even begin the project in the first place. Every solved problem exposed a more sophisticated one underneath it. The enclosure itself became a convergence point for design iteration, material science, experimentation, process refinement, printer modifications, structural assumptions, thermal management, and manufacturing strategy. The goal was never to create a decorative shell or visual mock-up. The goal was to manufacture a structural component capable of carrying a real astrophotography payload with confidence. And that changed everything. Material selection became one of the first major turning points. The enclosure needed stiffness, thermal stability, creep resistance, dimensional consistency, and long-term structural behavior. That ultimately pushed the project into a PA6 carbon fiber reinforced nylon material choice. And that material completely changed the rules. Nothing about the process was plug and play anymore. Moisture control, chamber stability, thermal management, adhesion strategies, flow consistency, extrusion behavior, and long-duration print reliability all became critical parts of this process. The printer itself had to evolve alongside the material. As the large format PA6 CF body print progressed, the process stopped feeling like hobby printing and started behaving more like active manufacturing under observation. The first large slab layers began accumulating enormous contraction forces inside the structure. And interestingly, the problem wasn't adhesion failure. The PA6 CF was actually bonding so aggressively to the plate that the internal stress accumulation began attempting to physically deform and lift the magnetic spring steel build surface itself. At that point, the printer was no longer being evaluated as simply deposited plastic. It had become a live thermomechanical system where the polymer, chamber environment, magnetic retention forces, geometry, and evolving stress state were all interacting simultaneously. Load cell telemetry unexpectedly became part of the diagnostic process. Originally intended only for probing and nozzle contact detection, it slowly evolved into a live equilibrium monitor for the structure itself. Visual inspection became equally important. Surface texture, perimeter reveal spacing, and wall behavior all became forms of telemetry. Over time, correlations started forming between the sensor behavior and visible stress accumulation. Mitigation strategies evolved dynamically as the print progressed. Additional retention clips were added to rebalance the mechanical loading on the spring steel plate. What started as a semi-serious improvisation quickly became what eventually earned the completely ridiculous name Clip AF. But it worked. They were chip clips that I had made a year ago, and they worked perfectly for build plate retention. As the structure transitioned upward into wall sections, internal supports, flange recesses, and mechanically interlocked geometry, the stress distribution changed dramatically. The enclosure slowly stopped behaving like a giant shrinking slab and started behaving more like a rigid composite shell structure. And eventually something changed. The failure stopped repeating. The chamber stabilized. Flow stabilized. The printer stopped fighting the material. The process entered equilibrium. And psychologically, that was a major turning point for me. Early in the project, every layer carried tension because previous failures conditioned the expectation that something hidden was waiting to go wrong. But eventually the feeling shifted from survival to confidence. The print was no longer getting lucky, it was repeating. And that distinction matters because repeatability is the moment where experimentation becomes manufacturing. And at that point, even the eternal deposition strategy had stopped being just a slicer setting and started becoming part of the structural design itself. The enclosure body was printed using fully solid monotonic linear infill with rotating layer directions specifically selected to avoid repeatedly stacking orthogonal stress planes throughout the structure. The process was no longer simply printing parts. It was engineering process behavior. Failures were also becoming increasingly physical. This was one of the more memorable ones. A lifted region had allowed PA6CF material to accumulate around the nozzle assembly, where it remained semi-molten during printing. Eventually, part of that accumulation detached and fell back onto the print surface. By the next toolpath pass, the material had cooled into a rigid composite obstruction. And unlike softer materials where the nozzle can often simply remelt through the defects, PA6CF behaved very differently. Once cooled, it stopped behaving like deposited filament and started behaving like hardened composite structure. At that point, the printer motion system had all the elegance of a crash test dummy in a rail-launched Volvo. But every failure refined the process further and quietly demanded a deeper understanding in return. Eventually, the manufacturing workflow stopped feeling experimental and started feeling repeatable. By the end of the enclosure process, HarmonicAF was no longer being produced through a single manufacturing method. The project evolved into a hybrid manufacturing workflow involving additive manufacturing, CNC machining, engraving, outsourced precision components, electronics integration, and process-controlled assembly preparation. And honestly, despite how far the project escalated, the final manufacturing cost ended up being far lower than most people would probably expect. One of the things that impressed me the most throughout this entire manufacturing process was just how capable PA6 carbon fiber nylon turned out to be for structural components like these. The material has an entirely different feel compared to more common printing materials. The stiffness, rigidity, thermal stability, surface texture, which I really love. It has this brushed carbon fiber look. Even the acoustic character of the parts feels different once they're in your hands. So it very quickly became obvious that this was the correct material for the enclosure and the structural system. So the enclosure body itself also became an opportunity to move beyond purely functional geometry and incorporate some visual identity. Constellation detailing and the integrated geometry, this monotonic construction for rigidity and strength, all the layered features all became part of the final design language. A lot of these details only became fully appreciated once the physical parts actually existed outside a CAD environment. And I'm really pleased with the way that everything turned out and the detail. And honestly, seeing all these systems finally laid out together for the first time was a pretty significant moment in this project, because this was the point where HarmonicAF stopped feeling theoretical. It got out of the CAD domain, and the design process had finally started manifesting into something physical. Most of the successes or failures of a project like this is determined long before anything's ever manufactured. The design phase is where assumptions get challenged, where constraints reveal themselves, where systems either begin converging together or quietly start fighting one another. Good manufacturing can only execute what the design process already understands. And for HarmonicAF, a huge amount of the project became learning how to think through these problems before material was ever placed on a machine. It was more than simply making parts fit together. It became more an exercise in understanding those parts' systems. Learning how to reduce complexity into smaller, more manageable problems became a huge part of HarmonicAF. Every assembly started simple: a rough idea, a sketch, a dimension. Those ideas slowly evolved through iteration. Sometimes that meant discovering better geometry. Sometimes it meant finding clearances that didn't work. Sometimes it meant realizing an entire approach needed to be reconsidered completely. The design process became less about drawing parts and more about understanding relationships between systems. How components interact, how assemblies move, how structure behaves, how packaging constraints affect everything around them. Parametric design became a huge part of that process because it allowed the project to evolve continuously as understanding improved. Subassemblies could be refined independently. Clearances could be validated before manufacturing. Interferences could be discovered early instead of after manufacturing. Over time, the project slowly transitioned from an individual part into a coherent mechanical system. Every iteration carried lessons forward into the next one. Not because the design process was linear, but because understanding compounds over time. Eventually, the assemblies stopped feeling experimental and started feeling intentional. That transition mirrors the larger story behind the project itself. The more ambitious the idea became, the more process demanded growth and return. A simple concept slowly evolved into something much larger than the original idea. Not just a harmonic drive mount, but a process of learning how to create one. In order to support working with the engineering filament, which is the PA6 carbon fiber, I had to make sure that my system here with the printer and supporting systems were able to actually work with this material, because it is by definition an engineering material and it has special needs in order to be able to work with it. Mostly related to temperature, but the filament itself is also quite a bit firmer and requires heat. So to begin with, it has to be very dry. I have it in auto mode right now. It's being held at 10% humidity. However, when I am actually working with the material and printing in the manufacturing process, I'll have the spool that's inside here, which is the carbon fiber material, at 80 degrees centigrade. And the humidity level on that will drop to about 3%, which is where you want it for actually running the manufacturing process. Then, in order to ensure proper feeding, this comes out and goes into a bank that I built. And this supports up to 4 different types of filaments. And filament will feed through and then out. But when filament retracts, rather than going back to the spool, it will go into the bank that extends down below. And that prevents filament from looping back onto the spool and causing issues with cross filament and tangles. And then when the filament gets pulled again through extrusion, it pulls from the bank until the bank is empty, and then it begins pulling off the spool again. And as it gets pulled through, it comes down to this device here, which is a multimedia extruder, which I built. And this has a servo, which controls different gates. I have up to 4 different types of filament gates here. And then it also has a stepper that drives gears that pull the filament from the spool and push it out all the way through the printer into the tool head. Then the tool head itself had to be rebuilt in order to support the temperatures needed for actually working with the engineering material. With the stock tool head, I was only able to run at 285 degrees centigrade, and I needed a minimum of 300. But with this upgrade, I was able to rebuild this and support up to 320 degrees centigrade. This also currently has a high volume hardened nozzle because the PACF filament is an abrasive material because of the carbon fiber that's within it, and it will wear out normal brass type of nozzles. So it needed a specialized nozzle as well. And additionally, I upgraded my build plate to Garolite, and this is a G10 build plate that I use with high temperature adhesive to adhere it to a spring steel subplate, and the spring steel attaches to the bed through the whole bed is magnetic, and so the build plate will adhere to it via the magnet. And with those upgrades, I was able to run the engineering materials successfully. So from here, the next phase shifts into post-processing, engraving, assembly, electronics integration. The next video in the series will focus heavily on assembly, mechanical integration, on-step configuration, and bringing HarmonicAF to life as an actual functioning system. Then after that, the plan is to move into no-load functional testing, debugging, load testing, and capacity validation, and hopefully, eventually, first light. And if everything behaves the way I'm hoping it will, all project files, documentation, bombs, and resources will eventually become publicly available through my GitHub once the system is stabilized through real-world validation. Even with the hybrid manufacturing process, carbon fiber composite enclosure, harmonic drive system, and equatorial base, HarmonicAF V2 ultimately came in at under $700 in total project cost, which honestly says a lot about what's becoming possible with modern manufacturing tools. So thanks so much for following along on this project and supporting the channel. If you enjoyed the video, definitely leave a comment below, because honestly, a huge amount of HarmonicAF version 2 exists because of ideas, feedback, and conversations from this community. So if you'd like to support the channel further, memberships and merch are available below as well. And if you want to follow the rest of the HarmonicAF journey, definitely subscribe and ring the bell so you don't miss the upcoming assembly and testing videos. One of the things I've realized throughout this project is that ambitious ideas have a way of changing the people who pursue them. Not because the process is easy, but because difficult projects force growth in ways comfort never will. So over time, the failures and iterations, problem solving, constant learning slowly compound into something larger than the project itself. And I think that's ultimately the real story behind HarmonicAF. Not simply creating something ambitious, but becoming more capable through the process of trying, transforming ourselves along the way. What you build transforms you. My name is Doug, and this is AstroAF.